Mud and scuffing have long been the bane of shoes and boots. In medieval times, wax was used to soften and waterproof leather footwear, but it had a dull finish. It wasn't until the early 20th century, with the invention of shoe polish, that footwear really started to shine. All it takes is a bit of polish and a lot of elbow grease. A vigorous brushing can enhance the job and help transform shoes from drab to fab. Shoe polish starts with mineral spirit solvent and different combinations of carnauba wax. The waxes go into a melter where they're heated to 260 degrees. The mixture cooks for 15 minutes while beaters keep everything blended together. This is dye fluid in a deep black shade. In another tank, the dye fluid and waxes are added to the solvent blend. Agitators mix it for 3 minutes. Tin container bottoms tumble down a chute and up a magnetic conveyor belt. A worker flips the tins right side up, then pushes them onto another conveyor. Once they're lined up, they're ready to be filled. Automated arms space the tins as they arrive at the filling head. The filling heads inject hot liquid shoe polish into the tins. The polish is precisely doled out so there's no spillover. The polish now needs to solidify, so the tins travel through a cooling tunnel. When they emerge, the polish is a thick paste. Workers perform a breaking strength test to be sure the final product has the right consistency. The polish-filled tins now funnel onto a conveyor that merges with a lid feeder. The feeder lowers the lids onto the tins. A compression wheel presses the lids in place with just the right amount of force. And this polish is now ready to shine. There's a different packaging system for liquid shoe polish. A blow molding machine forces hot air into plastic to form containers. Then, the mechanized rack holding the containers rotates and places the newly formed bottles on another conveyor. It moves them under a flame, which melts the rough edges. Revolving conveyors move under filling heads, which pump in liquid polish. Workers insert valves into applicators. Then, this machine press-fits the applicators onto the polish-filled containers. Using hydraulic pressure, another machine snaps clear domes onto the applicators. Rollers affix labels onto both sides of the bottles. The bottles then move through an inspection station. A mirror helps workers scrutinize the labeling job. A technician now takes a preliminary reading of the gloss on some leather. He applies some paste polish and rubs it in with a horsehair brush. He takes another reading, and the gloss on this leather has increased by a factor of 2, which means this polish passes muster and is ready to add some high luster to your footwear. The Mayans started using pots like these 2,600 years ago, probably for hot chocolate. They've evolved since then, and today, aficionados consider them essential for that perfect cup of tea. Silver-plated teapots come in many different styles, and making them requires the talent and skill of an old-world master. A century-old hand-circling machine cuts a perfect circle out of a brass sheet that's 6/100ths of an inch thick. Then, the disc heads to the press. After lubricating the press surface with vegetable oil, the disc is positioned and covered with a polyurethane stopper. As the press applies its 3 tons of pressure, the die moves upward, shaping the disc from underneath. The stopper, meanwhile, provides a counter-pressure to keep the die from breaking through the brass as it thins and stretches. They call this the draft shape. It then goes into another die that produces the final shape of the teapot's base. Next, they solder on the teapot rim, which was made the same way. A craftsman then hammers the metal to remove any imperfections left by the pressings, and punches in the maker's mark. Spinning is another technique used to form metal teapot parts. Here, a craftsman shapes a copper teapot mounted on a lathe. The metal is decorated using a technique called hand chasing. With a paper stencil, he applies the design in white powder. He pencil traces the pattern, then hammers in the design with a variety of tools. This intricate process requires the talented hands of an expert artisan. For the teapot spout, workers press brass plates into left and right side dies. A quarter-ton press produces the final spout shape. Soldering paste is brushed onto the halves. They're wired together, then fired to 600 degrees Fahrenheit. The spout gets an acid bath to remove all the impurities left behind from the soldering process. Workers polish the teapot with 3 progressively finer grades of pumice, which is crushed volcanic rock. One final buffing ensures the surface is perfectly smooth. With diamond-tipped hand tools, engravers can etch anything onto the teapot, from custom designs to company logos. Workers now screw on the lid, wire up the teapot, and immerse it in cleaning chemicals, followed by a silver plating bath. Just before shipping, they attach hardware and perform a final cleaning. Finally, the teapots are wrapped in acid-free cellulose to prevent the silver from tarnishing. It takes a highly skilled team of craftspeople to create these unique teapot designs, in styles ranging from Elizabethan to ultra-modern, beautiful and functional.
Skateboarding may have started out as a simple outdoor pastime, But in the last few decades, it's evolved into a popular thrill sport. Professional skateboarders are known for performing spectacular aerial maneuvers, achieving speeds and heights the early skateboarders could never have imagined. In the 1930s, thrill-seeking kids began attaching their metal roller skate wheels to wooden crates. Little did they know this would one day spawn a worldwide phenomenon. The boxes evolved to boards in 1958, when some California surfers invented sidewalk surfing, something to do when bad weather prevented them from riding the waves. They attached roller skate wheels to wooden planks, then coasted through the streets. Pretty soon, the fad caught on in cities throughout the United States. The deck, the part of the skateboard you stand on, is made up of several thin sheets of wood called veneers. Inexpensive boards use fewer sheets and lesser quality woods. These high-end boards use a full 7 sheets of top-quality maple. Only the top and bottom veneer sheets will actually show, so their exposed side is sanded smooth, and the other side gets a coat of glue. The inside sheets, meanwhile, go through the glue spreader, which saturates both sides. This adhesive is specially formulated to withstand vibration and shock. Workers stack 35 sheets of veneer, the equivalent of 5 skateboard decks, and place them in a mold. Skateboards vary in size and shape, so there's a different mold for each model. A press applies 44 tons of pressure, compacting the sheets and bending them to the shape of the mold. Excess glue squeezes out the sides, binding the 5 decks into one block. They'll be separated later. The block comes out after 3 hours. Now they drill 2 sets of holes through the block. These are for mounting the front and back trunks, the pivoting metal axles that enable the skateboard to turn. Now it's time to give the rectangular block a skateboard contour. They select a template in the general shape of the model they're making. It has pins underneath that fit snugly in the truck holes they've just drilled. This holds the template still while they do what's called the rough cut, sawing around the template leaving a 1-inch margin. Cutting off the excess separates the 5 decks. Now they contour each deck individually. Using a precise template, they run the deck against the cutting blade until they have the final shape. Now, using a router, they round off the top and bottom edges. Then they smooth all the surfaces against a drum sander. Now they switch to a buffer, which uses a combination of brushes and fine grit sandpaper to remove any rough wood fibers. The deck is now perfectly smooth. The next stop is the finishing room, where they first spray the decks with a colorless primer. This seals the pores in the wood veneer, so they won't absorb the coat of lacquer that comes next. The primer takes 2 hours to dry. Next, they spray on a coat of clear or colored lacquer. It leaves a protective high-gloss finish. The lacquer also takes 2 hours to dry. The final step of the finishing process is applying the decoration. The bold graphic designs are printed on plastic sheets. The skateboard factory either buys them ready-made or produces them in-house using its own silkscreen printing equipment. Workers center the design sheet, then feed the deck through a machine that applies heat and slight pressure simultaneously. The heat, 390 degrees Fahrenheit, induces a chemical reaction that melts the ink and lacquer. When the plastic comes off, the deck is finished. Decks of this caliber are sold unassembled in specialty stores. They're designed for serious riders who want to customize their skateboards. They pick and choose from different types of trucks, wheels, bearings, even the bolts that hold everything together. All these factors determine how fast or how fancy their skateboard will move and maneuver. If you have any comments about the show, or if you'd like to suggest topics for future shows, for the NHL, a regulation skating rink is 200 feet long by 85 feet wide. The rink is basic construction, but making the ice is an art. You have to get the thickness just right. If the ice is too thick, it'll tax the refrigeration system and soften on top. But if the ice is too thin, skate blades will cut right through it. The rink floor is a concrete slab. Covering it with ice begins in the arena's refrigeration room. There, a powerful compressor pumps refrigeration fluid, usually methanol or saline, through pipes running underneath the rink's floor. The concrete chills to between minus 15.8 and 18 degrees Fahrenheit, the temperature range required for water to freeze on concrete. This company made its own ice-making machine by retrofitting an ice resurfacer. Its onboard water tank feeds 20 sprayers that missed a 13-foot span. The water freezes within seconds. To make a quality ice surface, you have to build up the ice in layers, each about 7/100ths of an inch thick. Driving in the standard outside to inside oval pattern, each layer takes just 8 minutes. With 2 layers down, they paint the ice white. You'd think it would be simpler to just paint directly on the concrete, but the paint would chip off when they remove the ice at the end of the season. They would have to scrape and clean the slab before repainting it, a messy, expensive job. So instead, the ice maker mixes water and powdered paint in the onboard tank and sprays 3 layers onto the ice. This paint doesn't dry. Just like the water the machine sprayed before, it freezes into white ice. This metal dioxide-based paint is specially formulated for skating rinks, designed to cling to a base coat of ice. And unlike concrete paint, it's non-toxic and biodegradable, so that at the end of the season, the arena can melt the ice and let the water drain without contaminating the environment. Now a crew comes in to paint the hockey markings. Workers lay down string to mark the borders of the red line, the blue lines, and the goal lines. They elevate intersecting lines so that the paintbrush can pass. To paint the face-off circles, workers use an anchor, cable, and what's called a paint stick. It takes just 20 minutes or so to paint them. The paint is in a portable tank. It flows down the paint stick tube to a rectangular pad on the end. Now the goal crease at each net. First, they trace a template. Then fill in with the shade of blue you see in swimming pools. They use the same technique to paint the 8 red face-off spots. Back to the blue line. First, they spray water to freeze the strings in place. Then, using a brush on the same type of paint stick they use for the circles, they fill in the foot-wide space between the strings. Now for the home team's logo at center ice. After dabbing a mop in blue chalk, they run it over a computer-generated paper stencil of the logo. This transfers the design outline to the ice. They spray water on the chalk lines to freeze them in place, then paint the logo. Finally, with a garden hose, they spray water over all the markings to seal the paint. Then they slowly flood the ice with a larger hose for about a day and a half. This adds the final 1.1 inches of ice. The now skatable ice surface is about 1.6 inches thick, containing over 13,000 gallons of water, about 300 bathtubs full.
Snowblowers first came on the market in the 1950s, and before long, this alternative to shoveling really took off. Today's machines come in a range of sizes, from smaller models with 26cc engines to 50cc machines 3 feet wide for plowing through even the deepest snow. At the heart of a snowblower are rotating blades called augers. The left and right augers spiral in opposite directions in order to move snow toward the middle. There, a fan called an impeller swallows the snow and blows it out a chute. Each auger starts out as a blank, a partially formed steel disc a little less than 1/8 of an inch thick. This press finalizes the shape with about 200 tons of pressure. The bigger the snowblower, the bigger its augers. The press forms the left and right augers at the same time. Then, a blast of air ejects them onto separate conveyor belts. Next step, workers take a steel tube called a hub and mount it upright on an assembly jig. Then they take an auger and center it on the hub. The hub and auger then travel down a conveyor belt to a robotic welder. The robot fuses the two pieces into a single unit. Elsewhere in the factory, workers construct the steel housing that'll encase the augers. This housing consists of 4 parts: a cup to hold the impeller, a back piece with a hole for the cup, and 2 side plates. This bar aligns the pieces in a holder. First, everything turns upside down so the robot can access the back and weld the cup to the back piece. Then it flips right side up again, and the robot welds on the side plates. Total construction time, 55 seconds. The housings now undergo an electrostatic paint process. Powder paint laced with a positive electrical charge is drawn like a magnet to the housings, which have been negatively charged. Workers inspect the coat of paint and do any necessary touch-ups. Then the housings spend 15 minutes in an oven, which bakes on the paint. In another part of the factory, workers have bolted a gas-powered engine to a painted steel frame. Inside this frame, they assemble the transmission, the gear system that transfers power from the engine to the snowblower's wheels and augers. After bolting on the impeller, that black component in the back, they attach a large steel axle to the transmission-driven sprocket. Then they slide the now painted auger and hub units onto this axle. Now the housing arrives. Workers bolt the auger assembly into it. The impeller slides into the cup that's centered at the back of the housing. Then they screw the housing to the transmission frame. The last component is the snowblower's handle, where the control panel is mounted. There's a lever for selecting different speeds, and clutch levers that can be locked down to direct the wheels and augers. There's also a headlight so that you'll be visible to oncoming cars while clearing snow at night or on a snowy day. And of course, there's a lever that lets you choose the direction you want to blow the snow.